Right now, so Thiago, why won't you go and present?
Okay, so yeah, my name is Thiago. I'm from the Federal University of Paraná in Brazil, and so in this demonstration, I will show a proposal for selecting nodes from test beds in order to run distributed experiments on these nodes that are selected. And the goal for selecting these nodes is to increase the performance and repeatability of these experiments. So in this demo, I will visually show how our proposal works and why it is maybe better than other alternatives. And so an overview of how our solution works is it works basically in 3 steps. So we monitor all nodes on the test bed by measuring some pairwise metrics. Then we model all this data into an instability graph, what we call an instability graph, and then within this graph we search for certain structures that are the nodes, the selected nodes. Okay, so here an example of stability graph. This stability graph was generated by monitoring the Planet Lab testbed, which is a testbed that had several machines, several nodes distributed across the planet, so that we could run experiments in order to test new protocols and applications. Okay, so our monitoring on this testbed worked by measuring the round trip time, or the RTT, between each pair of nodes, and that is the biggest difference from our proposal to other alternatives that were already proposed. So other approaches, they measured and took into account features about the nodes, the nodes themselves, like CPU load or memory usage, or even some of them measure the RTT between the RTT, but from a single location to all others and not between each pair, as we are doing. So an edge between this, so in this stability graph, each vertex here is a Planet Lab node in this example, and an edge between nodes indicate that at least 90% of the measured RTTs are below a certain threshold in milliseconds during a certain time period, which are our 2 parameters for generating a graph. Okay, so in these examples that I will show, the size of these nodes are proportional to their degree. Okay, so the problem is, given this stability graph that we generated by monitoring RTT between nodes, how do we select a group of nodes to run these experiments with a better performance? So a very simple approach is to select some node with a very high degree and get all of its neighbors, for example, which is similar to running a ping from a certain location, which was a very common approach between researchers using the testbed. Okay, so I will show now a video here of this approach. So this simple approach, I'll select a node with a high degree there and its neighbors. Then these are all these nodes that were selected using this simple approach of selecting based on the degree and the neighbors. And then I'll organize the graph into clusters and now check the neighborhood of some of these nodes. And the problem with this approach here is that for some of the nodes that were selected, these nodes are not well connected, are not connected to most of the other selected nodes. And this could be a problem when you're running an experiment and some pairs don't communicate as well, and this can have a very huge impact on the performance of the experiment that you're running on these nodes. And this one here is a good example of that. So this node has a very high degree. However, it is not connected to most of the other selected nodes. And so now, so then our proposal is to search for a K-core in this stability graph, and a K-core is basically a set of nodes that form a graph with a minimum degree K. So the idea is that the selected nodes have at least K edges between themselves. And so we try to maximize what we call the connectivity. We want a very well connected group to run our experiments. And running experiments on this on nodes selected by this approach, we significantly increased the performance and repeatability of our experiments when compared to the experiments run on nodes selected by the degree, as I showed, or for running a ping from a certain location, or based on the features of the nodes themselves, like CPU load, for example. I would now have a video for here. So now the K-core strategy. So this the nodes in red are the K-core that was selected, and I'll take a closer look on just this K-core and see the neighborhood of some of these nodes to compare with the other approach. Okay, so here these nodes have edges to most of the other selected nodes, and that's why as these edges represent better a certain level of stability between the nodes, so that's why our experiments had increases performance. Thank you.
Thanks. It's interesting, especially when you want to repeat some experiments. Probably this is useful. Although network condition may change even in Planet Lab, and when you run twice or second time one experiment, you end up with different clusters, correct? So
yes.
Also because, well, probably the problem is not that big in this case because nodes are static. You don't have mobile nodes in there. Am I right?
Okay, yeah. So the thing is, this stability graph is generated based on a time period. So you say, like, I want 1 hour of the last 1 hour of monitoring, then we get all the data from the last 1 hour, generate the graph and select the nodes, and then run the experiments. If 1 hour later you want to run another experiment, then you do all this process again. So we are continually monitoring and generating this. So it's a dynamic graph in this regard. Yeah.
But it's dynamic to which point? Probably every 15 minutes or every hour you can do it again. But if you have a mobile node or if you have a set of mobile nodes, probably not even a minute is enough.
Yeah, this was designed with the Planet Lab testbed in mind. So or any testbed that works the same. So it's fixed nodes. They don't move. It's just a testbed for network protocols and experiments. So
yeah, no,
not so much for mobility. Yeah, it definitely would not work. Yeah.
Well, it would be different. But fundamental question. So when do you need to have a stable graph of the topology? I mean, the fact that you have a changing topology in the internet is because this is the way it is. So if you want to test a protocol in the natural environment in which you will run, now you have to take into account that you will have instability. So in which sense having stable behavior helps in your experiments, at least? I have some answers, but I want to know what's your point of view.
Well, we had some problems when running. For example, one professor there, he's working with hypercube topology, and he wanted to run some distributed experiments for. I can't remember the algorithm, but it was a distributed algorithm. It was trying to check the properties of his topology and virtual topology, so an overlay. And then he was not able to complete his experiments because of some of the nodes couldn't communicate as well with other, and then his experiment was just hang. And so when you're not interested in this kind of having this instability, then this would be useful. So because you want to be able to finish your experiments. But yeah, you are right. So because for some applications, you want to test on a stable environment because this will be the real environment that your application will run. So, and that would be like a future work because based on this, because the way our proposal works, we can select the opposite, right? You can try to select an unstable set of nodes if you want to run experiments. So I'm showing here a strategy to select a stable set of nodes, but you can use the exact same graph and monitoring strategy to select an unstable. Yeah.
Yeah, I guess you can tune your mechanism with some parameters, and then you can decide if you want it more compact or more sparse or more with higher connectivity in some nodes. I mean, I guess it's something that is tunable in your
yeah. So it's basically how you generate this graph and how you search for nodes in that. Yes.
How fast is it? How fast is it in getting this graph? I mean, what are the numbers you're talking about? The plot you showed before, I guess it's just something that you put in. I don't know if those were real Planet Lab nodes, because there are thousands of Planet Lab nodes. So how many of those do you use?
Oh yes, the examples that I showed were based on actual data from Planet Lab, but only 200 or 300 nodes, not all of them. And so to download data and select nodes using that KKR strategy was about 1.5 minutes, 2 minutes. And if you wanted, for example, to select nodes using click algorithm, then it would take a bit longer. But that's because of the computational complexity of the algorithm. Yeah.
Okay, it's not too long. I mean, you can run this in a semi-automatic way in order to generate a topology when you need it, and then use it for 10 minutes probably. So spending 1 minute, it's not that much in that case. Thank you very much.
Thank you.
Okay. Well, I think it also brings today and Thiago's slot. I see already this next presenter, Qiong Zhang, joined. So maybe it's a good transition point. Any chance to do? Can you stay around for the next demo, or you need to go to the poster tracks?
I need to go to the other posters because the second posters are almost done in 10 minutes. I have a couple of minutes for each. So I'll be back in 20 minutes or so. Okay.
Okay. So I'll stop now the recording. So recording zone. Maybe you can introduce yourself and then proceed with your demo, at least with the first driver.
Okay. Thank you. Good afternoon or good morning, everyone. My name is Qiong Zhang, and these are my co-authors. And we are from Fujitsu Network Communications in USA and Fujitsu Laboratories Limited in Japan. And this demo, we will show a blockchain-based protocol for federated learning. Okay, I need to use my... So what is federated learning? Federated learning is a distributed machine learning approach which enables machine learning models training on decentralized private data. It usually involves a central server and a group of clients. And it can have hundreds of training rounds when converged. And here we show 3 basic steps in a single training round. Step 1, a federated learning server sends a global machine learning model to a group of clients. Step 2, clients get the global model and train it with local data, and then provide a local model to the server. And step 3, the server gets local models and aggregates them to a global model. And this figure shows the federated learning server aggregates received local models from clients using approach such as weighted averaging. So here we have local model X1 and number of training samples P1 at client and at a federated learning client 1, and the local model X2 and number of training samples P2 at client 2. So once the federated learning server receives those machine learning models, they will calculate a new global model based on this equation. So we can see here that the federated learning preserves data privacy by training local models on private data locally, and also it can save network bandwidth by exchanging machine learning models between the clients and the server instead of transferring a large amount of raw data in a centralized place for training. Here we focus on cross-silo federated learning, where organizations act as Federated Learning server clients and share a common incentive to train a machine learning model based on all of their data. In this case, Federated Learning server and clients are physically distributed at different organizations, usually. So there are challenges. First is to establish secure network communications between Federated Learning client and server. And second challenge is how to authenticate the Federated Learning server or Federated Learning clients to join a Federated Learning training task. And third is how to track each Federated Learning steps, each training round at each client and each server for auditing purposes. And there are many other challenges which we can find in the paper below. But in this demo, we focus on these three challenges. The challenges led us to consider a blockchain-based platform for data exchange developed in Fujitsu called VPX. VPX stands for Virtual Private Digital Exchange. In this system, there is a blockchain network with many peer nodes, and this blockchain network is established based on Hyperledger Fabric platform. And here, each peer node on the blockchain network is corresponding to a Federated Learning client or a Federated Learning server, and each peer has a consistent copy, a local copy of the blockchain. And for a specific Federated Learning task, Federated Learning client or server can write the description of a local model or global model, we call it the metadata of the model, to the blockchain by the metadata publish function. And those Federated Learning client or server can also search whatever metadata on the blockchain at the local copy using the metadata get function. So once the metadata is found and you find, okay, this is the metadata for the desired machine learning model I would like to have, then we can use the data get function to exchange machine learning models between Federated Learning client and server. And the data get function establishes a secure network connection between a Federated Learning client and server. And here we see the blockchain recording the metadata. And in this system, basically, the data to exchange are the machine learning models. And for more details of this system, you may find them in the presentation below. And please note that there are actually many other functions available in VPX, but here we only use these three major functions, and they are developed as smart contract in Hyperledger Fabric. So based on the three functions in VPX, we propose a blockchain-based protocol for Federated Learning. And here are the steps. First, at the Federated Learning server, the server writes initial global model metadata to the blockchain using the metadata publish function. And step two, the Federated Learning clients keep reading the metadata and checking the metadata from the blockchain using the metadata get function. And in the meantime, it checks if a new global model, excuse me, if a new global model is available. If no, go to step two. If yes, it gets the global model from the server using the data get function, and then it performs local training on the local data set. And then after finished the local training, it writes metadata for the new for the local model to the blockchain using the metadata publish function, and then go to step two, continue checking if there is any new global model available. And then step 7, the Federated Learning server also continue checking and read the metadata from the blockchain using the metadata get function to see if the number of available local models meets a threshold. If no, it goes to step 7. And if yes, it gets local model updates from the selected clients using the data get function. And then it aggregates those local models to a new global model, and then writes the metadata of the global model back to the blockchain. And then a new training round will start. And please note that only the metadata of machine learning models are written to the blockchain. Basically, the description of the machine learning model written to the blockchain. And the actual models are directly and securely transferred between Federated Learning server and clients. So there are several advantages for this proposed protocol. First, it tracks Federated Learning steps with immutable records, basically are those metadata on the blockchain. And second, it transfers only selected machine learning models between Federated Learning server and clients, and based on the consensus or the metadata on the blockchain, indicating the availability and the quality of those machine learning models. Then it enables the client selection without transferring unnecessary local models to the server. As you may know that in the traditional Federated Learning approach, so after clients finish local training, they will send their local models to the server without knowing that if their local models will be used or not by the server. Third, it simplifies the underlying network configurations for Federated Learning server by taking advantage of security features provided on the blockchain platform, like our date get function. And it is extremely important if the Federated Learning clients and the server, they're physically apart. And here is the demo configuration. We have two servers here. One is VPX server for the blockchain network, and one is the machine learning server for a neural network model training on the public minister dataset for demonstration purposes. And for the machine learning server, we create two clients, Federated Learning clients, and one Federated Learning server, and they are all running as a Docker container. And on the VPX server, we construct a blockchain network with 3 peer nodes, and each peer node is corresponding to a Federated Learning client or a server. And we can see that the Federated Learning client can write neural network model metadata to the blockchain. In the meantime, they will read the metadata from the blockchain. And in the meantime, the Federated Learning client and server, they can exchange neural network models between each other. Okay, are there any questions so far?
Thiago, do you want to ask something, or should we go further?
Oh yeah, I'm the only one here. Okay, yeah, yes, I would like to ask something.
Sure.
Could you comment on the trust model that you are considering here, or maybe give some example as a motivation? So maybe I didn't get it right, but you said that a possible use case for this was a company with several branches physically apart from each other, and they want to aggregate the machine learning models. So, but then if it's the same company, then each part of each branch, each physically apart server is trust each other. So why do you need the blockchain protocol? If you, I mean, what the blockchain is adding something that more traditional approach, like a database, for example, would add to record all this metadata.
First, compared to database, this one using the hashing, right? It's immutable records using blockchain.
Mm-hmm.
And the third is that this system has the description of the model first. You search the description of the model and see if it's qualified what I need. And then it transfer the model. So which is different from traditional Federated Learning, where you transfer the local model no matter, or global model no matter they want it or not. So this one is just like I take my own pace, and the server can select whatever I want and transfer it. Or the local clients, if they say, okay, I'm busy right now, I don't want to do it, I don't transfer. And if I want to do it, and I transfer. Yeah, I join the learning. Yeah.
Okay, so but then you said immutable record. Yeah, that's okay. But if it's the same company, why do you need immutable? I mean, yes, I guess if you don't want someone to go to join your system and screw with your record, so I mean that's partly the reason you want this immutable record. Okay, yeah, okay, I see it. So thank you.
Yeah, another one is it's possible to apply this to asynchronous federated learning. In that case, actually, if you have those tracking of the, one is for auditing purpose, another one is you tracking it, you will know which round of models I need. So a tracking mechanism is needed for asynchronous federated learning in that case.
Okay,
yeah.
Thank you.
Okay, Qiong, then maybe we can proceed with the demo itself.
Sure.
So that we can see it.
Okay. So now can you still see my screen with the 4 windows?
Yes.
Okay. So here we have 4 windows. This window is the server. I need to move in here, the configuration for the server. And here is the client, the 2 clients, client 1 and client 2. And this one shows the records on the blockchain. And here I written some metadata of the model to the blockchain for testing this morning. And you may also see that in the beginning, there are 3 user registration records on the blockchain. So basically, we need to register the 3 the 2 federated clients and the federated learning server to the blockchain for for authentication and registration purposes. And those API pub is whatever using the metadata publish function, and then the records metadata will be written to the blockchain. And you may see here in the federated learning server, the configuration, we have a node ID. We make it as a 0, and it has 2 clients. And the requirement is the number of required clients is 2. So basically 2 of them have to join. And then we also can assign a federated learning task. Here we make it as we can make it here as a neural network 1 that for our testing for this task. So basically this task means that that when we train neural network, we need to adjusting those hyperparameters, right? And here each neural network model for training can assign a federated learning task name, and they can share the same blockchain network. And here we're making a number of rounds. If you want, we can make it federated learning training rounds to be 10, for example. Or if you want to see the result earlier, the accuracy may not be may not be high. We make it 5 if we want to see the result earlier. And in the client, we can see that this client has node ID 1. And he is appointed the server ID that he should connect to is 0, and same federated learning task name. And this one shows the local training, the number of epochs for the local training, which is 5. This one shows in the local data set, the number of training per client is training samples is 20K, and the number of testing samples is 3,000. And similarly for the client 2. And now let's start to run. We call that here 13 is the current metadata record. Then we start the server. So you may see in the server in the beginning, it writes the initial global model to the blockchain. So you can see on the blockchain, the number 14 record block number is shown. Let's click this block number and you will see those metadata in here. And this is the unique transaction ID generated based on the task name, the federated learning task name. Okay, now let us start client 1. Hold on. It is running. Okay, client 1 is running. So it's doing the local training with right now it's a third epoch. Similarly, we will start client 2. It take a while. And you will see client 1 is doing the local training. Okay, client 2 also starts the local training. And you may see the block number 15 is written to the blockchain. It is from the client 1 because client 1 write the blockchain, write the metadata of the local model to the blockchain. And here, the server continue reading the blockchain and to check if there are enough clients publish the metadata. I think the client 2 finished local training also, so the server received the all the local models from the 2 clients, and then it aggregates the result. And receive the global model. It receives the global, all the local model aggregated, and then let me check. Yeah, then it write the metadata of the new global model to the blockchain. So it's I think it's block 17. And here should be the client 1 local training for round 1. This is also client 2 local training for round 1. Yeah, the server is continue checking the availability of the local models. And so client 1 finished the local training. So a new block is block 18 is written to blockchain, and client 2 also. So block 19 for the client 2, and you will see this is the aggregation result for the client 1. And you will see at that time, because the metadata for the local model also includes the training accuracy and testing accuracy and training loss and the testing loss. So the server in the meantime also aggregate using weighted average to aggregate those training loss and accuracy. So it obtain this data, training loss and training accuracy, testing loss and testing accuracy for the global model at round 1. So we're still at round 2 training. So it take a while for each training round. So client 1 finished training. So here the server say client clients received so far is 1, and then client 2 finished. So then again, here is the aggregated result. And you can see the testing accuracy is increased. It's getting better after each round. So any questions while we are waiting for the
Yes, I think
training rounds to finish?
Bean and Thiago were here all the time. Aditi joined after the introduction, and June joined just recently. So please go ahead and ask. So.
Yeah, I have a very nice demo, and actually, I'm not an expert of on both of the topics, but actually, I do have some very probably layman's question. Excuse me if those are very naive questions. So the first question is that the whole idea of this blockchain, right, is this distributed ledger, right? So the do away with the centralized government, the bank, or whatever those intermediaries sitting between different customers. And but here I see you introduce this centralized aggregation server in order to coordinate the different learning, on different clients. So my question is certainly just a very high-level architectural question. So how does this really fit into the basic idea of this distributed ledger, and without any intervention of the centralized entities?
Actually, here for demo and because this is our first paper for this project. Can you hear me clearly? Because I hear you a little jitter. I think because of my simulation here. Actually, we have a centralized server here just for following the basic concepts of federated learning. And actually, we can have a selection of server in the system. Because again, using distributed ledger, actually each peer can be can have possibility to be a server. And we can have some selection or using a digital identity to identify a server. Those are all possible. But here it's just for simplicity.
So the communication between the client server and the aggregation server is the data or is the update of the model? If I understand correctly, that is the model update.
Yes, right? It's the updated model. Yeah, not the raw data. Correct.
Not the raw data. Okay. So then the in this block, I see on your upper right, this is the block list. So this block list is maintained in where? Is maintained
in a blockchain network. Actually, in another server. Yeah. Maybe later I will present the demo to you, the demo slides to you again, so you will have better understanding of it. Yeah.
All right. Okay.
So we have two servers basically. One server running the blockchain network, and another server running those federated learning clients and the server.
Got you. All right. Yes, this makes sense. Thank you. Very nice. Okay.
Well, I'm not sure how much more time we'll have, because I think the slot will be over in 12 minutes. So hopefully Vincenzo will come back. So you might want to just go ahead and show whatever you want. Oh, actually, Vincenzo is right
actually, the
here.
training stopped. Okay. So I will show the demo. Yeah, again. Okay. So this is the result, round 4. Yeah. So because we start from round 0, so this is the end of the 5th round, and we can see that at the final round, the accuracy is already 0.99, and the testing accuracy is 0.97. Because here the data is not a non-IDD data, so the accuracy is very similar to the centralized training accuracy. Okay, let me show the demo again, the demo slides again.
Yeah, so maybe just for the sake of time, since we have about 10 minutes left, maybe I think the introduction itself was about like 10 minutes. So maybe it's better to split it half and half, maybe just to give a general idea about the approach and then show a little bit of a demo.
Okay, so should I start with the proposed approach?
For what are you proposing blockchain here? What is the scenario you want to sell the blockchain idea here? It's just to connect remote offices or what?
Okay, so it's here.
Yeah,
and basically the scenario is it's connecting doing the federal learning among different organizations, and actually it can be for different even in the same organization for different office branches. Because another advantage of federal learning is that it can save network bandwidth by exchanging only machine learning models instead of a large amount of raw data. And the purpose of this system actually is to try to solve those challenges. One is to establish secure network communications between federal learning clients and the server, because that when we exchange machine learning models, and there may be some attackers able to getting those machine learning models, and those local models actually is able to the attacker may do reverse engineer to obtain the details of the private data. So it's very important to have a secure communication when they exchange machine learning models. And another one is for authentication, and to authenticate the federal learning clients and the server into a federal learning task. And this one authentication actually is naturally built in blockchain instead of you build another different application authentication system. And another obvious advantage of blockchain is to track the federal learning each step, each training round at each client and each server for like auditing purposes or for asynchronous learning in the future. And
if I can ask a question, so here you need blockchain because the different actors cannot trust each other, or for which reason? I mean, I understand blockchain offers a lot of solutions, but authentication and tracking, also secure communications can be obtained in other ways. So if you don't have any basis for trust, I may understand you want to go to use blockchain. So in this case, is that really necessary? Maybe it is, but I may miss that point.
Trust, first is if it's a federal learning, across silo federal learning is across different organizations. So for that purpose, when you're doing the federal learning, you need to have trust, and the blockchain will help, right?
And you cannot use any centralized version of this. I mean, you can have different organizations that rely on a third party that guarantees trustfulness, for instance.
Actually, this question has been asked before also. Basically,
here,
the central server and basically the central server here, for simplicity, we assume there is a central server, federal learning central server here. Mm-hmm. And actually, in reality, you can using the blockchain to validate or to select which one can be our federal learning server. And based on other mechanisms of blockchain, such as a digital identity. And you can select whichever server you trust and everybody trusts, and then to start a federal learning.
I see.
Yeah.
Okay, thanks.
So Qiong, do you want to show a little bit of the demo to the newcomers, to Vincenzo, for example?
Okay, so the demo configuration, basically we have two servers. One is a VPX server for the blockchain network. Another one is machine learning server for training neural network model on the main data set. So in the machine learning server, we have two clients and one server. Each of them is running as a Docker container. And in the VPX server, we construct a blockchain network with the 3 peer nodes, and each of them is corresponding to a Federated Learning client or server. And now let me show the demo. So
you can do whatever you want. I'll trust. I cannot read what is there.
oh, it's too small. Let me increase the font.
No, it's fine. Don't worry.
Okay.
It looks like something real, so that's good.
So do you want to see the demo, or you want to see the slide?
Oh, no, the demo is fine. The demo is fine. So explain me what this is doing. So you have three clients and one VPX server. And do you try to introduce some misbehavior or something that you can show how to no?
Here we do not introduce any misbehavior. We just start a neural network training and using the blockchain to show those metadata each time when a local training model or global model ready, and it read the metadata of those local models is written to the blockchain. So the advantage of our approach using the blockchain, another one I would like to show here. First is the tracking of each step for auditing purposes. And the second one is actually for our blockchain, we write the description of the machine learning models. We call it the metadata of the machine learning model to the blockchain instead of the whole model. And by doing that, basically, we only need to transfer selected models between the Federated Learning server and clients based on those metadata. So basically, you can search whatever machine learning model you desire on the blockchain based on the metadata. So once you find the metadata of that machine learning model, you say, okay, that's the one I want to join, or that's the global model I want to train, or the task I want to join. So then you can further request model transfer from the client, from the server, or from the client. So basically, we think this approach is it can avoid many unnecessary model exchange compared to the traditional Federated Learning.
Yeah, this is interesting. On the other side, I guess using blockchain will incur some costs. So have you evaluated the costs?
Yes, there are costs because underlying the blockchain, we have many signaling, like a commit. There are many steps in commit a transaction. But what we consider is that it simplifies the Federated Learning client and the server processes. And also, you do not have to build additional security or encryption, decryption mechanism, because here is whole suite. Blockchain can provide a whole suite of security features for you. So for the clients and server and using this system, they only need to use 3 basic functions, which is metadata publish. You write the metadata to the blockchain, and you get the metadata, you're checking what's available, machine learning models available from the blockchain, and you're getting it from certain client or server based on the metadata. So you only need to use 3 basic functions, and only this several steps, then you can finish one training round of Federated Learning, and all the security features are provided already.
I had a question, Aditya.
Sure.
I have a question for the demo. When I joined, you were just training, and the updates in the blockchain was from number 14, and then when the training finished, it went to number 28. So how often does the client update? In what instances do the client update to the blockchain?
Okay. How often basically is based on the training speed, right? How fast this local the clients can train the local model. So once the local model finished training, it is finished the training, then the client will write the metadata for the local model to the blockchain. So that's where it shows. So once it finished local training, it will write the metadata of the local model to the blockchain. Yeah.
Okay. Thank you. Thank you for clarifying.
Mm-hmm.
So are there any more questions for Qiong? Well, we are on time pretty much, and I expected kind of multiple repeats of the short speech. Instead, we had one long session, so I think it was highly informative. So does anybody wants to ask anything or talk about anything before we conclude?
Just small curiosity. I wanted to ask if you see the system going to market anytime soon, because there's a request, there's demand for this kind of security, but still everyone who knows about blockchain outside the engineering world is thinking of money, electronic money, and things like that. So this is quite different application of it. So is it something that can go to market, or is it?
Okay, consider you mean electricity money. Do you mean that the power of work, that kind of a consensus protocol when you're running the blockchain?
I'm asking if you think that some companies are gonna implement a system like VPX for any business, real business they want to run to make money.
Right now, VPX has one demo in Japan. You will watch the presentation here below, and basically they have one demo in Japan, but in that use case, it's exchanging data, not machine learning models. So now we step one further, so we exchanging machine learning models for federated learning. And regarding federated learning applications, right now many applications, real applications for federated learning is in healthcare field. In healthcare, so basically when people doing the cancer imaging, so to analyze those images, if positive or negative, and they using machine learning to do that, and because those images are private at the different hospitals, and they try to training models from the data for the data from different hospitals. So in that case, it is highly possible in the future to realize.
So as of today, your customers are basically health systems, I guess. Most of the money will come from there and the revenue, but Fujitsu, I guess, will target more markets in the future.
We are actually we are actually from Fujitsu Network Communications. So our application is to try to find applications in telecom, in network. So we are looking for applications there, and that's what our current research task. One of them.
Sounds very interesting.
Yeah, applied to telecommunication networks.
Yeah. Sounds interesting. Probably also for control, for kind of extending. The control of virtualized networks. This could be the sharing learning processes may be very, very important, and that's very critical also to be robust to attacks and to any kind of trouble. So this may have future. Yeah, I think.
Yes.
So thank you very much.
Thank you.
Yeah.
Okay.
Thank you.
So, Vincenzo, since you are one of the chairs, so should we close the session?
Yeah, I think it's been a marathon for me, because I've been jumping from one presentation to another, asking questions here and there, and now I'm a bit confused. I guess probably next question I will ask my wife will be something mix about virtual reality and switching and migration of virtual machines rather than I don't know what, because now I'm a bit confused. But it's nice to see such a nice amount of work which is coming and is getting ready for more important publications, because I see work like this and many others I've seen in the posters and the demos today may soon go to more complete papers and be published and exposed to a larger audience. So thank you very much to the authors, and congratulations to everybody for your work.
Thank you.
Okay, thank you all. Thank you very much. It's nice meeting you all.
Yes.
Have a good day.
Thank you. Thank
Thank you.
you. Bye.
Bye-bye.
Bye-bye.